Hello mathematicians, we're now going to have a look at evaluating integrals using integration by parts. Now this is a very neat little technique based on the product rule of differentiation. So it's worth taking our time to get our heads around it, and then eventually as we become familiar with it, it will become hopefully as automatic as the product rule and the quotient rule. So if we have a product, uv, each of which are functions of x, then we know that the product rule says put down the first, differentiate the second, plus put down the second, differentiate the first. And now, if we just rearrange that to make this the subject, that will become u dv dx equals d dx of uv minus v du dx. We're then going to integrate right through all terms on both sides of the equation. So the integral of u dv dx with respect to x equals the integral of d dx of uv with respect to x minus the integral of v du dx with respect to x. And of course the integral of the differential, so the integral of the differential of uv just yields us uv, and then we have this, that u times dv dx with respect to x equals uv minus v du dx with respect to x. Now you're not given this formula, unlike the formula for the product rule and so on. This is a shortcut version of it, but it's slightly dangerous. All that we have to do, I think, really is to practice it to make sure we get our head around how the layout of the problems work. And then it's a good straightforward process. So if we think about this technique, where we can use it is where, first of all, we have a product. So the expression to be integrated can be separated into two parts, one of which needs to be easily integrated, because our aim is to obtain a simpler integral than the one that we had to start with. So sometimes we might need to mentally check which substitution to make. Occasionally the process will need to be repeated, and sometimes it will even yield the original integral again, and that gives us an equation that we have to solve. So we just have to have faith in the process, do it carefully, and understand what it is that we're doing. So let's apply it to a couple of examples. Look at our two things here. We have an x and a log of x. Now that we know that log of x can't be easily integrated. In fact, to date, we would say that it can't be integrated at all. So that makes our choice of what to work with relatively easy. Now, if we lay it out in the fashion of this thing up here, our first step is to rewrite our integral. So it's the integral of u, so this will be our u, log of x, which I'll just write that, dv dx, so I need to be able to integrate this, so I know that the integral of x is x squared on 2, and then my v is going to be, or my dv dx is x. So this is dv dx, this is u, and I then have the integral of u dv dx dx, and that's going to equal u times v, so that's log of x times v, which was x squared on 2, so x squared on 2 log of x, minus the integral, it's going to run into the next space, minus the integral of v, so again my v is x squared on 2, times du dx, so du dx is the differential of log x with respect to x, which will be 1 on x dx. So I've got x squared on 2 log x minus, now this will become the integral of x on 2 dx, which will become x squared on 4 plus c. Now I could tidy that up by taking out common factors. No, I suppose I should. So if I take out x squared and 4 as a common factor, I could have taken 2, but it wouldn't have looked so nice. Then that becomes 2 log x minus 1 plus c. So let's consider our integral here of x e to the x. Now both parts of this are easy to integrate, the x and the e to the x. So how do we know which one to continue with? Well, it's a little bit of trial and error, but often it's the e to the x. It's about all that I can say to you at this stage. If we pick the wrong one, then we'll probably discover it fairly quickly as we go through it. So let's rewrite our integral now as the integral of x times d dx of e to the x dx. So following our formula up above, that means that we're looking at x times e to the x minus the integral of e to the x times the differential of x, which is of course 1, dx. So the reason we went, one of the reasons we went with the e to the x here is because it just keeps repeating, but we were able to get rid of the x when we differentiated. So when we do this, we've got x e to the x minus e to the x plus c, and I guess it's tidiest if we take e to the x outside of x minus 1 plus c. Okay, so for our next example, again, both parts are easy to integrate. So once again, it's probably just practice with questions that helps you to make the decision here. So I'm going to choose to write it as x times d dx of sine x dx, because then when I differentiate the x, it will disappear. So that will become uv, which is x sine x, minus the integral of v du. So that's differential of x, which is of course just 1. So I get that, which I can do. So x sine x minus, and the integral of sine, of course, is going to be cos, except of course it will be x, and it will be minus, which will make this a plus out here, and then plus c. Now we might try these others in class, and I'll just jump down a little bit further. So if we look at this one here, I'm going to rewrite that as the integral, that's blue now, the integral of x squared times d dx of e to the minus 3x on minus 3 dx. So that will give me uv, which is x squared e to the minus 3x on minus 3 minus the integral of e to the minus 3x on minus 3 times the differential of this, which is 2x dx. And if we tidy that up a little bit, and I'll do that with the magic pen again, just so that I can save a bit of space here. I haven't left much. So if I take this minus 3 out the front, that will make plus, and the 3 will go down to the bottom. And take the 2 out the front, so I've got plus 2/3 out there. And I'll just try to rub that out neatly. So if I then shuffle across here a little bit, we've got minus x squared e to the minus 3x on 3 plus 2/3 of this integral now, x times e to the minus 3x. So again, we'll do our integration by parts formula to that. So I'll rewrite my x times e to the minus 3x as again x times d dx of e to the minus 3x on minus 3 dx. And you can probably see why, because I want this x to disappear next. So that will give me minus x squared e to the minus 3x on 3 plus 2/3 of uv, so that's x times e to the minus 3x on minus 3 minus the integral of e to the minus 3x on minus 3 times the differential of x, which is of course 1 dx. And when I do that, I've got minus x squared e to the minus 3x on 3, it takes a long time to write all this stuff, minus 2/9 x e to the minus 3x. And if I take that minus and take this third out the front, that'll be plus 1/3 the integral of e to the minus 3x, which will of course become the integral of minus e to the minus 3x on minus 3, which changes this to minus 1/9. So if I fix that up, plus c. Now there are some problems where, not many, where we sort of have a fix. So we know that there's no way that we can integrate log, for example. So we do a bit of a fix so that we can use integration by parts by introducing a constant, which in this case is 1. So we're going to rewrite our integral as the product of 1 and log x so that we can use integration by parts. And we know that 1 is easy to integrate, so we can write this as log x times d dx of x dx. So that will become x log x. This log, of course, is the natural log, so I could be writing ln. So x log x minus the integral of, and it's x times the differential of log x, which is 1 on x, if it's the natural log, dx, which of course becomes the integral of 1, which is x, so I've got x outside of log x minus x, or x outside of log x minus 1, plus c. Now the last one I'll do here is this one, for two reasons. One is obviously it's a nasty question, and also it's got the limits on the integral, so just to show what we do there. So if I take my integral here, and while x is easy to integrate, the thing is that I can't integrate sine to the minus 1 of x anyhow, so I really don't have a choice to make. So I need to write this as the integral of sine to the minus 1 of x times d dx of x squared on 2 dx. So that's going to give me x squared on 2 times sine to the minus 1 of x from 1 to 0. So I need to put those limits on my uv part, minus the integral from 0 to 1 of x squared on 2 times the differential of sine to the minus 1. And I can do that as standard integral table tells me that that's the answer. Now this part here I will evaluate, so when I put the 1 in here I've got a half sine to the minus 1 of 1, which is pi on 2, so half pi on 2 will give me pi on 4, minus, when I put the 0 in I've got 0. And then minus this integral here, 0 to 1, I'll actually take this 2 out the front just to make it look less cluttered. So half x squared on the square root of 1 minus x squared dx. Now you might hark back to earlier on where we said if we've got one of these, then one thing to try is to do a change of variable where we work on the rational part. So I could let u equal 1 minus x squared, but it will make the bottom nicer if I let u squared equals 1 minus x squared, so that the bottom will then just become square root of u squared, which is u. So something nice and simple which I could divide through by if necessary. So when u squared equals 1 minus x squared, then if I do implicit differentiation, that will give me that 2u du dx equals minus 2x, and divide through by the negative 2. So u du is minus x dx. But because I don't have the minus over here, if I make that a plus and that a minus, and I come back to my equation over here, being careful not to lose that pi on 4 or the half anywhere, and remembering I'll have to do something with these limits in a moment, then in here, my x squared dx, if I can take x dx of that and replace it by minus u du, and the x that's left up the top, well, from this I get that x squared equals 1 minus u squared, so x is square root of 1 minus u squared. So I have square root of 1 minus u squared, and on the bottom I've got the square root of u squared, which is just u. So that and that cancel out. This minus and that minus go and give me a plus. Now I have to do something about the limits. So when x equals 0, that implies that if x equals 0, u equals 1. So I've got a 1 down here, and when x equals 1, that implies that u equals 0. So I've got a 0 up here. Now, normally I would say, well, we would take these, switch them around again and change the sign, but that's where there's a little trick. Well, it's not a little trick, I think it's a big trick when you're under pressure in an exam. So I've got half of the integral from 1 to 0 of the square root of 1 minus u squared du. At this point, the trick is that I've got to recognise that square root of 1 minus u squared is the positive semicircle for a circle of radius 1 centered on the origin. So that means that the value of that integral there, which I could normally only integrate by now doing a trig substitution, which we're not up to yet, I have to evaluate from a knowledge of the curve. So from a knowledge of the curve, I can see that the area of the positive semicircle, circle of radius 1, sorry, it's not even the full semicircle because it's just going from 1 to 0. So it's only that much, so it's a quarter of the semicircle. So that's 1/4 of pi r squared, where r is 1, so it's a quarter of pi, and I want a half of a quarter of pi, so that's an eighth of pi, so all up my answer is 3 pi on 8. Not nice.